Hello there, and welcome to the Sleep Lab, where tonight we're going on an extraordinary journey that will take you back through time itself, all the way to the very beginning of everything we know and love. You might think that the earth beneath your feet, the air you breathe, and the water you drink have always existed in their current form, peaceful and stable. But that's not what happened at all. What we're about to discover is that our planet is actually the survivor of an almost unimaginable series of cosmic catastrophes, violent collisions, and near-total annihilations that should have destroyed any chance of life existing here. Every breath you take, every drop of water you've ever consumed, every piece of ground you've ever walked on is the product of 4.5 billion years of chaos, destruction, and miraculous recovery. If we don't understand how our planet formed from cosmic dust and violence, how it survived being completely frozen solid for 15 million years, how it recovered from mass extinctions that wiped out 95% of all life, and how it somehow created the perfect conditions for everything we see today, then we can't truly appreciate just how rare and precious our existence really is, or why Earth might be the only home to life in the entire universe. If you enjoy these kinds of deep, contemplative explorations into the mysteries of our world, if you like drifting off to sleep while pondering the incredible forces that shaped our reality, then you found exactly what you're looking for. Consider subscribing to the Sleep Lab and giving this video a like, because we specialize in taking these profound cosmic stories and presenting them in a way that lets your mind wander through deep time while your body finds the rest it needs. Tonight, we're traveling back 4.5 billion years to witness the birth of our world and discover why, against all odds, we're here at all. Let's move to our first part of the documentary. The story we're about to tell begins in a place where there is no story at all. No Earth, no moon, no life, no solid ground beneath your feet. Just emptiness, punctuated by a young, violent star we now call the Sun, surrounded by nothing but cosmic dust and debris. It's almost 5 billion years ago, and if you could somehow exist in this space, you'd find yourself floating in what looks like a vast, chaotic construction site where gravity is the only architect, and time is measured not in human lifespans, but in the slow, patient accumulation of millions upon millions of years. The Sun, at this point, is barely recognizable as the stable, life-giving star we know today. It's a newborn stellar furnace, still settling into its nuclear rhythm, surrounded by the leftover materials from its own violent birth. This isn't the organized solar system we learned about in school, with planets neatly arranged in their predictable orbits. This is cosmic chaos, a swirling disk of dust, gas, and rocky fragments that extends far beyond where Earth's orbit will eventually stabilize. The dust particles are unimaginably small, microscopic grains of silicon, iron, carbon, and other elements forged in the nuclear hearts of ancient stars that exploded billions of years before our sun was even a whisper in the cosmic darkness. But here's where the story becomes almost magical in its simplicity. Gravity, that invisible force we barely notice as we go about our daily lives, is about to perform one of the most remarkable construction projects in the universe. These tiny dust particles, each smaller than anything you could see with your naked eye, begin to stick together when they collide. It starts slowly, almost gently. Two particles of cosmic dust drift into each other in the vast emptiness, and instead of bouncing apart, they cling together. Then a third particle joins them, and a fourth, and gradually, over spans of time that dwarf all of human history, these microscopic specks grow into pebbles, then rocks, then boulders, then asteroids. The process is both incredibly violent and remarkably patient. As these growing chunks of matter orbit the young sun, they slam into each other at tremendous speeds. Some collisions destroy both objects, sending fragments spinning off into space, but others result in growth, with the smaller object being absorbed into the larger one, adding its mass and momentum to the growing planetary embryo. Picture a cosmic game of billiards, played with rocks the size of mountains, where the table stretches across millions of miles, and each shot takes thousands of years to complete. Over the course of perhaps 50 million years, these countless collisions and accumulations gradually clear the space around the sun, with the largest objects growing ever more massive as they sweep up everything in their orbital paths. It's a process astronomers call accretion, and it's happening not just where Earth will eventually form, but throughout the solar system. The outer regions are cold enough for water and other materials to freeze, allowing the formation of much larger planets like Jupiter and Saturn. But in the inner solar system, where temperatures are higher due to the sun's heat, only rocky materials can survive, setting the stage for the formation of Mercury, Venus, Earth, and Mars. But even after this initial period of accretion, even after a recognizable planet has begun to take shape in the orbit we now call home, the story is far from peaceful. The early Earth, roughly 4.5 billion years ago, is nothing like the blue and green world we know today. It's a hellscape that would make the surface of Venus seem hospitable by comparison. The temperature at the surface exceeds 2,000 degrees Fahrenheit, hot enough to melt copper and turn rock into flowing rivers of lava. There is no breathable atmosphere, no protective ozone layer, no magnetic field to shield the surface from radiation. The air, if you could call the toxic mixture of gases surrounding the planet air, consists primarily of carbon dioxide, nitrogen, and water vapor, creating a greenhouse effect so intense that the entire planet glows like a coal in a furnace. This early Earth spins on its axis much faster than it does today, completing a full rotation in just 6 hours, which means that the sun rises and sets every 3 hours in a dizzying cycle of scorching day and equally scorching night. The rapid rotation creates winds of unimaginable violence, atmospheric disturbances that would make the most powerful hurricanes in recorded history seem like gentle breezes. The entire planet is essentially one massive ocean of molten rock, with no solid surface, no continents, no islands, just an endless sea of lava stretching from pole to pole. But the violence is far from over. Somewhere else in the solar system, another planet is taking shape, a world roughly the size of Mars that astronomers have named Theia. This planet, following its own chaotic orbital path around the young sun, is on a collision course with Earth. The impending impact isn't a gentle merger or a glancing blow. It's a head-on collision between two planetary bodies traveling at speeds of nearly 25,000 miles per hour, 20 times faster than a bullet fired from a high-powered rifle. When Theia finally strikes Earth, the collision is so violent, so utterly devastating, that it defies human comprehension. The impact releases energy equivalent to millions of nuclear weapons detonating simultaneously. Both planets, all the solid matter that had taken millions of years to accumulate through the patient work of gravity and accretion, instantly liquefies. The collision sends shock waves racing around the Earth at speeds that would circumnavigate the planet in minutes. Trillions of tons of molten rock and vaporized material blast out into space, creating a debris field that extends far beyond the Earth's atmosphere. For a brief, terrifying moment, it appears as though the entire project of planetary formation has been undone, as though the early Earth has been completely destroyed. The debris cloud is so massive, so energetic, that it seems impossible anything coherent could ever emerge from the chaos. But once again, gravity begins its patient work. Over the course of roughly 1,000 years, the ejected material doesn't escape into the void of space. Instead, it forms a ring of superheated dust and rock fragments orbiting the newly reformed Earth, a ring so dense and extensive that it would make Saturn's rings look like a thin line of smoke. From this ring of cosmic debris, something remarkable begins to coalesce. The same forces of accretion that originally formed the planets now work to build something entirely new: our moon. Chunk by chunk, collision by collision, the ring material gravitationally attracts itself into an increasingly large spherical body. Within perhaps 10,000 years, a relatively brief moment in cosmic time, the moon has formed, but it's nothing. Like the distant, serene companion we see in our night sky today. This early moon is terrifyingly close to Earth, orbiting at a distance of just 14,000 miles instead of the current 240,000 miles. It appears enormous in the sky, a looming presence that dominates the heavens and creates gravitational effects that are almost impossible to imagine. The close proximity of this massive moon creates tides of incredible violence. On the few areas where the Earth's surface has begun to cool and solidify, enormous waves of molten rock race back and forth across the landscape, pulled by the moon's gravity into tidal bulges that rise and fall like liquid mountains. The Earth's rotation continues to slow under the moon's gravitational influence, but it's still spinning far faster than it does today, creating a world where the rapid alternation between the moon's gravitational pull and its absence generates constant seismic activity. But even as this cosmic violence continues to reshape the planet, the conditions necessary for the next chapter of Earth's story are slowly falling into place. The surface, despite its hellish appearance, is beginning to cool. The constant bombardment of space debris that characterized the earliest phases of planetary formation is starting to diminish as the solar system gradually clears itself of the leftover material from its birth. And most importantly, the cosmic collisions that continue to pummel the young Earth are beginning to deliver something that will prove absolutely essential for everything that follows: water. The meteorites and comets that rain down on Earth during this period aren't just chunks of rock and metal. Many of them contain crystals that look deceptively simple, like grains of salt. But these crystals hold within them tiny droplets of water that has been frozen in the cold depths of space for millions of years. Each individual meteorite carries only a small amount of water, but the bombardment continues relentlessly for over 20 million years. And gradually, as the Earth's surface cools enough to allow liquid water to exist, pools begin to form. It's difficult to overstate the importance of this cosmic delivery system. Every drop of water you've ever consumed, every ocean wave, every raindrop, every ice cube in your freezer, every tear you've ever shed is composed of water molecules that are billions of years old and may have traveled millions of miles through the void of space, carried inside meteorites, before finally arriving on Earth during this violent early period. The water that flows from your tap today is the same water that helped to create the first oceans on a young, hostile planet that bore no resemblance to the world we now call home. As the bombardment continues and more water accumulates, the Earth's surface undergoes another crucial transformation. The molten rock begins to cool and solidify into a thin crust, the planet's first attempt at creating solid ground. The atmosphere, still toxic and unbreathable, hovers around 170 degrees Fahrenheit, which is scalding by human standards, but cool enough to allow the water to remain liquid rather than boiling away into space. The first primitive oceans form in the low-lying areas of this newly solidified crust. But these are oceans unlike anything we could imagine today, surrounded by active volcanoes, constantly stirred by earthquakes, and filled with minerals and chemicals leached from the surrounding rock. The close moon continues to exert its gravitational influence, but gradually, over millions of years, it begins to move away from Earth. The same tidal forces that initially created such violent effects also slow the Earth's rotation and cause the moon to spiral outward into a more distant orbit. As this happens, the massive tides begin to calm. The constant seismic activity diminishes, and the planet starts to achieve a kind of rough stability. About 700 million years after the planet's formation, roughly 3.8 billion years ago, Earth has begun to look recognizably like a planet rather than a molten ball of rock. Water covers much of the surface, and scattered throughout these primitive oceans are small islands of solid rock, volcanic formations that have risen from the seafloor through the constant geological activity that continues to reshape the planet. These islands seem to appear from nowhere, popping up through the ocean surface as molten rock from the Earth's interior forces its way upward through cracks in the crust, cools in contact with the water, and gradually builds layers of solid land. These early islands are the ancestors of the continents, the first attempts at creating large-scale solid ground on a planet that has been dominated by liquid rock and water. Over time, these individual islands will be pushed together by the movement of the Earth's crust, eventually forming the first true continents. But even at this early stage, Earth has achieved something remarkable and rare in the universe. It has both water and land, the basic ingredients necessary for the complex chemistry that will eventually give rise to life. Yet despite these promising developments, the planet remains utterly hostile to anything we would recognize as life. The atmosphere is still toxic, dominated by carbon dioxide and other gases that would be lethal to any modern organism. The temperature, while cooler than during the molten rock phase, is still scorching by biological standards. The radiation from the young sun, unfiltered by any protective atmosphere, bathes the surface in lethal doses of ultraviolet light. Most importantly, the chemical conditions necessary for life simply don't exist yet. The complex molecules that form the basis of biological processes haven't had a chance to develop in this violent, rapidly changing environment. But the stage is being set for something unprecedented in the history of the solar system. The water that has been delivered by cosmic bombardment will provide the medium in which the first chemical reactions leading to life can take place. The solid ground will provide mineral surfaces where complex molecules can form and concentrate. The cooling atmosphere will eventually reach temperatures where delicate chemical processes can operate without being immediately destroyed by heat. And perhaps most importantly, the gradually stabilizing conditions will provide enough time for the slow, patient work of chemistry to transform lifeless rock and water into the first stirrings of something that might, billions of years in the future, grow into the complex biosphere we see around us today. The first chapter in Earth's story, the chapter of cosmic violence and planetary formation, is drawing to a close. What comes next will be even more remarkable. The emergence of life from the chemical soup of the early oceans, a development so improbable and so transformative that it will change not just the surface of the planet, but the entire atmosphere and the very nature of what it means for a world to be alive. But that transformation won't happen quickly, and it won't happen easily. It will require conditions so precise and circumstances so delicate that the wonder isn't that life emerged on Earth, but that it managed to survive and flourish in a universe that seems designed to extinguish it at every turn. Let's move to our second part of the documentary, the birth of life against all odds. If you thought the violent formation of Earth was dramatic, what happens next in our planet's story is even more extraordinary. We're about to witness something that, as far as we know, has only happened once in the entire universe: the emergence of life itself. But this isn't the gentle, nurturing process you might imagine. Life doesn't arrive on Earth through some peaceful, gradual awakening. Instead, it emerges from the most hostile, toxic, and seemingly impossible conditions you could imagine, in places so extreme that they would kill any modern organism in seconds. Let's travel back 3.8 billion years to a time when Earth has finally developed its first permanent crust, but still looks nothing like the world we know. The surface temperature hovers around a blistering 170 degrees Fahrenheit. The atmosphere is a poisonous cocktail of carbon dioxide, nitrogen, and water vapor, with not a molecule of breathable oxygen anywhere to be found. The skies are perpetually dark, filled with volcanic ash and toxic gases. Massive storms, far more powerful than any hurricane we've ever experienced, rage across the planet's surface, whipped up by Earth's incredibly fast rotation. Remember, at this time, a full day lasts only about 10 hours, and the moon looms so close to Earth that it appears 3 times larger in the sky than it does today, creating tides that race across the landscape like moving mountains of water. But it's beneath the surface of the newly formed oceans where the most remarkable story begins to unfold. Thousands of feet below the waves, in a world of absolute darkness, where the crushing pressure would flatten any surface-dwelling creature, something extraordinary is taking shape. Picture this underwater landscape, a seemingly barren ocean floor, cold and lifeless, stretching endlessly into the black depths. But then, rising from the seafloor, like alien monuments, you begin to see structures that seem almost supernatural. These are hydrothermal vents, underwater chimneys that spew superheated water and chemicals into the freezing ocean. Here's how these remarkable formations work. Seawater seeps down through cracks in the Earth's crust, diving deep into the planet's interior, where it encounters the incredible heat of the molten rock below. As this water heats up, it dissolves minerals and gases from the surrounding rock, creating a potent chemical cocktail. Then, under immense pressure, this mineral-rich water shoots back up through the ocean floor, creating towers of deposited minerals that can grow to be hundreds of feet tall. The water emerging from these vents is superheated, sometimes reaching temperatures of over 750 degrees Fahrenheit, hot enough to melt lead. But these vents aren't just geological curiosities. They're about to become the crucibles of life itself. Remember those meteors that have been bombarding Earth for millions of years, the same ones that delivered our planet's water? Well, they've been carrying more than just H2O. As these space rocks dissolve in Earth's oceans, they release a treasure trove of organic compounds. Carbon, the building block of all life as we know it. Amino acids, the basic components of proteins. Complex organic molecules that have traveled millions of miles through the vacuum of space to reach our young planet. Now, imagine these organic compounds from space mixing with the mineral-rich, superheated water erupting from the hydrothermal vents. You have the perfect recipe for something unprecedented. A chemical soup so rich and complex that it contains all the basic ingredients needed for life. It's impossible to know exactly how or when it happened, and scientists are still debating the precise mechanisms today. But somehow, in these deep ocean laboratories, chemistry becomes biology. Organic molecules begin to organize themselves into increasingly complex structures. Simple chemical reactions give way to self-replicating systems. And finally, after millions of years of chemical evolution, the first living organisms appear in Earth's oceans. These aren't the complex creatures with eyes and limbs and sophisticated behaviors that we're familiar with. These are single-celled bacteria, so tiny that millions of them could fit on the head of a pin. They have no consciousness, no ability to move purposefully, no complex structures. They're barely more than sophisticated chemical reactions wrapped in simple membranes. But they have one absolutely crucial characteristic. They can reproduce themselves. They can take raw materials from their environment and use them to create copies of themselves. This is the fundamental definition of life, and it represents the most important transition in Earth's entire history. For hundreds of millions of years, these microscopic organisms remain the only life on Earth. They exist in the deep ocean, around the hydrothermal vents where life first emerged and gradually spread to other parts of the sea floor. But Earth is still a hostile world. The atmosphere remains toxic. The surface is bombarded by deadly radiation from space, and the climate is wildly unstable. These early bacteria are tough, capable of surviving in conditions that would be lethal to virtually any modern organism. But they're also limited. They exist, they reproduce, they spread slowly through the oceans, but they don't really change the planet around them. But then, about 3.5 billion years ago, something revolutionary happens. Evolution produces a new kind of bacteria, one with a capability that will ultimately transform not just life on Earth, but the entire planet itself. These organisms, called cyanobacteria, develop the ability to photosynthesize. They figure out how to harness the energy of sunlight and use it to manufacture their own food from simple chemical ingredients, carbon dioxide and water. This might not sound particularly dramatic, but photosynthesis is actually one of the most sophisticated chemical processes in biology. It requires complex molecular machinery that can capture light energy and convert it into chemical energy with remarkable efficiency. The fact that life developed this capability so early in Earth's history is truly extraordinary. But what makes photosynthesis even more significant is its byproduct. When cyanobacteria use sunlight to convert carbon dioxide and water into glucose, they release oxygen as waste. At first, this oxygen doesn't accumulate in the atmosphere or oceans. Instead, it's immediately absorbed by iron dissolved in the seawater, creating iron oxides that fall to the ocean floor as rust-colored sediments. For millions of years, the oceans act like a massive sponge, soaking up all the oxygen that the cyanobacteria produce. But slowly, inexorably, the oxygen levels begin to rise. The cyanobacteria are incredibly successful, forming massive colonies called stromatolites that look like underwater gardens of living rock. These mounded structures, some reaching several feet in height, are actually composed of billions of individual bacteria working together to capture sunlight and produce food. The stromatolites become incredibly abundant in Earth's shallow seas, and for over 1 billion years, they pump oxygen into the water and atmosphere at an ever-increasing rate. This oxygen isn't just changing the chemistry of the oceans and air, it's literally rusting the planet. Iron in the oceans turns to iron oxide and settles to the bottom, creating distinctive red and orange bands in the rock record that geologists can still see today. These banded iron formations are like Earth's signature, marking the period when oxygen-producing life first began to reshape our planet's chemistry. But we're still billions of years away from complex life as we know it. For most of Earth's early history, the only living things are these simple, single-celled organisms. They're incredibly important because they're creating the oxygen that will eventually make complex life possible, but they themselves remain relatively unchanged for enormous spans of time. To put this in perspective, if Earth's entire history were compressed into a single year, life would appear in early spring. But complex multicellular organisms wouldn't show up until mid-November. During this incredibly long period of bacterial dominance, Earth undergoes massive changes. The continents are constantly moving, pushed around by the slow but inexorable forces of plate tectonics. Volcanic islands rise from the ocean floor and eventually collide with each other to form the first supercontinents. The atmosphere continues to change as oxygen levels rise and carbon dioxide levels fluctuate. The climate swings between warm periods and ice ages, driven by changes in Earth's orbit, the amount of greenhouse gases in the atmosphere, and the arrangement of the continents. But it's around 750 million years ago that Earth faces its most extreme test yet. The same geological forces that have been slowly rearranging the continents reach a critical point. Heat from Earth's core causes the supercontinent Rodinia to begin breaking apart, stretching and weakening the crust until massive volcanic eruptions tear the landmass in two. These aren't ordinary volcanic eruptions. They're flood basalts, where enormous volumes of lava pour out of the ground, sometimes covering areas the size of entire countries with molten rock thousands of feet thick. The volcanic activity pumps massive amounts of carbon dioxide into the atmosphere, but it also has an unexpected side effect. As the continent splits apart, vast areas of fresh rock are exposed to the atmosphere for the first time. These newly exposed rocks begin to absorb carbon dioxide from the air through chemical weathering, pulling CO2 out of the atmosphere faster than the volcanoes can replace it. The result is a catastrophic drop in atmospheric carbon dioxide levels. Carbon dioxide is what's called a greenhouse gas. It traps heat from the sun and keeps Earth's surface warm. But with CO2 levels plummeting, the planet begins to lose its ability to retain solar heat. Over the course of just a few thousand years, global temperatures drop dramatically, falling from a comfortable 85 degrees to a bone-chilling minus 60 degrees Fahrenheit. This is the beginning of what scientists call snowball Earth, and it represents the closest our planet has ever come to becoming completely lifeless. The cooling begins at the poles, where ice sheets start to form and spread. But this isn't like a normal ice age. The more ice that forms, the more sunlight gets reflected back into space instead of being absorbed by the planet's surface. This creates a runaway effect, where cooling leads to more ice, which leads to more cooling, which leads to even more ice. Within a relatively short period, ice sheets thousands of feet thick begin to spread from both poles toward the equator. For 15 million years, Earth becomes a giant snowball, with ice up to 2 miles thick, covering the entire planet from pole to pole. The ice reflects virtually all of the sun's energy back into space, making the planet even colder. Temperatures drop so low that even the equatorial oceans freeze solid. From space, Earth would have looked like a brilliant white marble, completely covered in ice and snow. It seems impossible that life could survive such conditions. These early bacteria and cyanobacteria had survived meteor bombardments, toxic atmospheres, and extreme temperatures. But snowball Earth presents a challenge unlike anything they've faced before. With the entire ocean frozen solid and virtually no sunlight reaching the surface, photosynthesis becomes impossible. The stromatolites that have been producing oxygen for over 1 billion years are entombed beneath miles of ice. It appears that Earth's first experiment with life might be coming to an end. But life is more resilient than it appears. Deep beneath the ice, around the same hydrothermal vents where life first emerged, some bacteria managed to survive. These organisms don't depend on sunlight for energy. Instead, they derive their nutrition from the chemicals spewing out of the underwater vents, living in a world that's completely cut off from the frozen surface above. For 15 million years, these deep-sea survivors represent virtually the only life left on Earth. Meanwhile, even though the surface is frozen, Earth's interior remains hot. Volcanoes continue to erupt beneath the ice, pumping carbon dioxide into the atmosphere. But with all the rocks buried under ice, there's nothing to absorb the CO2 anymore. Gradually, over millions of years, volcanic emissions begin to build up a blanket of greenhouse gases in the atmosphere. Eventually, this volcanic carbon dioxide reaches levels so high that it begins to trap enough solar heat to start melting the ice. The end of snowball Earth is as dramatic as its beginning. As the ice starts to melt, it exposes dark rock and ocean water that absorbs sunlight instead of reflecting it. This creates another runaway effect, but in the opposite direction. Melting leads to more heat absorption, which leads to more melting, which leads to even more warming. The transition from a completely frozen planet to a warm, ice-free world happens remarkably quickly in geological terms, probably within just a few thousand years. But the melting ice brings an unexpected gift. While Earth was frozen, the sun's ultraviolet radiation was reacting with water molecules in the ice, creating hydrogen peroxide, a compound rich in oxygen. As the ice melts and the hydrogen peroxide breaks down, it releases massive amounts of oxygen into the atmosphere and oceans. This oxygen boost, combined with the return of photosynthesizing cyanobacteria as the oceans warm up, creates conditions that are perfect for a new chapter in Earth's story. By 600 million years ago, the atmosphere has warmed to temperatures similar to a pleasant summer day, and days have lengthened to about 22 hours as Earth's rotation continues to slow down. The oceans are filled with oxygen, and the planet has all the ingredients necessary for something unprecedented: the evolution of complex, multicellular life. The bacteria that survived snowball Earth emerge into a world that's been completely transformed, and they're about to begin an evolutionary explosion that will change life on Earth forever. The stage is now set for one of the most remarkable events in the history of our planet. Those simple, single-celled organisms that have dominated Earth for billions of years are about to give rise to creatures with multiple cells, specialized organs, and capabilities that would have been impossible in the early Earth. But before we can witness that incredible transformation, we need to understand just how close we came to having no story at all. Snowball, Earth reminds us that life on our planet exists in a delicate balance, and that the difference between a thriving biosphere and a lifeless frozen ball is smaller than we might think. Let's move to our third part of the documentary, Explosions of Life and Mass Extinctions, where we'll witness how our planet became a stage for the most dramatic evolutionary leaps and the most devastating catastrophes in Earth's history. After 15 million years trapped in ice, Earth finally broke free from its frozen prison, and what emerged was a world transformed beyond recognition. The ice had done more than just preserve life beneath its frozen surface. It had actually created the perfect conditions for life to explode into forms more complex and varied than anything the planet had ever seen. As the last of the great ice sheets melted away 600 million years ago, the atmosphere warmed to something like a pleasant summer day, and the days had stretched to about 22 hours long. But most importantly, through a series of chemical reactions that occurred while the planet was frozen, massive amounts of oxygen had been released into the oceans and atmosphere. This wasn't just any oxygen. This was oxygen in concentrations that would allow life to grow larger, more complex, and more ambitious than ever before. When we peer into those ancient oceans 540 million years ago, expecting to find life struggling to recover from the greatest freeze in Earth's history, we instead discover something miraculous. Those primitive bacteria that had somehow survived the big freeze had not just endured, they had evolved. Scattered across the seafloor were plants and something else entirely, something that looked like an armored slug taking up residence among the underwater gardens. This creature, called Wiwaxia, represented a new generation of complex multicelled organisms, and it was just the beginning of what scientists call the Cambrian explosion, one of the most dynamic periods in our planet's entire history. The increased oxygen levels that resulted from the melting ice allowed creatures to grow larger and develop bony skeletons for the first time. Suddenly, the oceans were full of worms, sponges, and most remarkably, trilobites, distant relatives of insects, lobsters, and even scorpions. These weren't the microscopic bacteria that had dominated the seas for billions of years. Life in the oceans had blossomed from microscopic organisms into genuine monsters. There was Anomalocaris, nearly 2 feet long with large eyes, razor-sharp teeth, and grasping limbs that made it the ocean's first super predator. All it had to do was take its pick among the slower creatures that couldn't defend themselves. The trilobites, with their soft bellies exposed, were easy prey for these new hunting machines. But perhaps most significant of all the creatures emerging during this explosion of life was something called Pikaia, only 1.5 inches long, but possessing what may have been the first spine in Earth's history. Over millions of years, this simple structure would evolve into the spine that keeps every vertebrate standing, including us. We're looking at the oceans, expecting to find life in ruins after the planet's greatest catastrophe, but instead, discovering that life had not just survived, it had used the crisis as an opportunity to reinvent itself entirely. Beneath the waves, there were already tens of thousands of plant and animal species, and the advance of life seemed unstoppable. As the continents continued their slow dance around the globe, a new landmass called Gondwana had formed by 460 million years ago. The temperature was a comfortable 90 degrees, and oxygen levels were close to what they are today. Logic would suggest that the land should have been covered with plants and crawling with creatures. But when we examine these ancient landscapes, there's not much there besides a few patches of algae. The reason for this apparent contradiction is simple but deadly. The sun itself was the problem. At this point in Earth's history, our star was blasting the surface with deadly radiation that made it impossible for the complex life thriving in the oceans to survive on land. But 30 miles up, where the sun's rays first entered Earth's atmosphere, something remarkable was happening that would change everything. When oxygen met the sun's radiation in the upper atmosphere, it transformed into another kind of gas called ozone. This ozone began forming a blanket around the planet that absorbed the lethal radiation before it could reach the surface. Over 120 million years, this ozone layer grew thicker and more effective, gradually reducing the amount of dangerous radiation that reached Earth's surface. Without this protective shield forming exactly when it did, life on land simply wouldn't exist. It's one of those perfectly timed coincidences that make Earth's story seem almost impossibly orchestrated. Once this radiation shield was in place, life finally had its chance to colonize the land. The first pioneers were small, mossy lumps, the first true land plants. And just as their ocean-dwelling ancestors had done, these early plants began pumping out even more oxygen, causing atmospheric levels to soar even higher. By 375 million years ago, something extraordinary was swimming in the ancient waters. A strange fish called Tiktaalik that would change the course of life on Earth forever. This remarkable creature could use its muscular neck to raise itself up out of the water, and most importantly, its fins functioned as primitive legs, allowing it to move onto dry land. This represents one of the most important moments in the making of our planet, the transition of life from water to land. Over the next 15 million years, creatures like Tiktaalik continued to evolve, growing stronger limbs and spending more time out of the water, where plant life was exploding in diversity and abundance. By 360 million years ago, their relatives, called tetrapods, had made the land their permanent home. From these four-legged vertebrates would eventually evolve dinosaurs, birds, mammals, and ultimately humans. Every backbone you see in the animal kingdom today can trace its lineage back to these pioneering creatures that first dragged themselves out of ancient seas. The plant kingdom was undergoing its own revolution during this period. There were mosses and ferns everywhere, some growing at least 100 feet tall, creating the first true forests. But the most significant innovation was something that seems almost trivial: the humble seed. Until this point, plants had reproduced using spores, single-cell particles that needed plenty of water to grow. But seeds were different. These embryonic plants came with their own food and water supply, meaning they could survive far from water for months or even years. This simple innovation allowed plant life to spread across continents, and each new tree and plant continued pumping out oxygen, creating an atmosphere richer in this life-giving gas than Earth had ever known. The world that emerged from this explosion of innovation was unlike anything we see today. It was a planet of giants. Dragonflies called meganura soared through the skies with wingspans rivaling those of eagles, their hunting territories extending over vast areas. Down on the ground lived millipedes 6 feet long and scorpions the size of wolves. This wasn't just random gigantism. It was the direct result of oxygen levels being much higher than they are today, which allowed the respiratory systems of these creatures to be far more efficient, fueling their bodies to grow to monstrous proportions. The arthropods that were among the first to colonize land hundreds of millions of years ago looked almost identical to the bugs that invade our homes today, except they were scaled up to nightmarish sizes. During this period, another crucial evolutionary innovation appeared that would secure life's foothold on land permanently. Until this time, animals had been laying their eggs in water, tying them forever to aquatic environments. But a lizard-like creature called Hylonomus developed something revolutionary: eggs that contained all the water and nutrients that developing offspring needed. These babies could grow in their own self-contained aquatic environment, allowing animals to leave the water behind entirely and conquer the land. This innovation led to the rise of reptiles and represented another major step toward the complex ecosystems we know today. But even as life seemed to be conquering every corner of the planet, the stage was being set for disaster. Inevitably, with so much life came death, and dead plant matter began building up and decaying into dense, soggy layers. Over hundreds of millions of years, rock layers buried these organic deposits, and heat from Earth's core combined with pressure from overlying rocks to transform these ancient forests into seams of coal. Every lump of coal we burn today is made of plants that died 300 million years ago, a direct connection between our modern energy consumption and these ancient forests of giants. As evolution continued its relentless march forward, small lizards evolved into giant reptiles. In the lush landscapes of what would become Siberia, herds of massive creatures called Scutosaurus grazed peacefully. These distant relatives of turtles were impressive herbivores, but if these plant eaters looked formidable, the carnivores were absolutely terrifying. Gorgonopsids were perfectly engineered prehistoric killing machines, using their saber teeth to wound their prey, and then patiently watching as their victims weakened from blood loss before moving in for the final kill. This was a world where life had seemingly mastered every challenge Earth could throw at it. Complex ecosystems stretched across continents, the atmosphere was rich with oxygen, and evolution had produced an incredible diversity of species adapted to every possible environment. Life had not just survived the planet's earlier catastrophes, it had used them as stepping stones to reach unprecedented levels of complexity and abundance. But as these predators stalked their prey across ancient landscapes, something was stirring deep beneath the planet's surface that would make all previous catastrophes seem minor by comparison. The ground began to grow hot beneath the feet of these ancient creatures. Enormous pressure was building beneath the surface, and suddenly, lava began spewing into the air. But this wasn't the eruption of a single volcano. This was something far more terrifying. The entire landscape was erupting in what scientists call a flood basalt eruption, where massive plumes of mantle material rise up from deep inside the earth and push molten rock out through fissures in the crust across enormous areas. The lush paradise that had taken millions of years to develop became a lifeless hell in a matter of decades. The Scutosaurus and Gorgonopsids were among the first casualties in what would become the greatest mass extinction the world has ever seen. the Permian extinction. But this was just the beginning of a catastrophe that would spread far beyond the initial eruption zone. On the other side of the supercontinent Gondwana, thousands of miles away from the volcanic devastation, it appeared to be snowing despite temperatures around 70 degrees. But it wasn't snow, it was ash. Fallout from the eruptions carrying death around the globe. The ash burned and suffocated animals worldwide, but that was only the first wave of destruction. Sulfur dioxide from the eruptions filled the atmosphere, and when it rained, this gas turned into sulfuric acid that burned everything it touched. What had begun as a local disaster had transformed into a global catastrophe that would reshape life on Earth. The Siberian eruptions increased atmospheric carbon dioxide levels dramatically, causing the atmosphere to heat up, water to evaporate, and vegetation to die on a planetary scale. Life on land was being systematically wiped out, but the oceans weren't safe either. As the crisis deepened, the waters turned an ominous pink color as most marine life disappeared. The heated atmosphere had warmed the oceans and stripped them of oxygen, creating vast dead zones where only hardy pink algae could survive in the stagnant water. The Siberian eruptions had transformed the entire planet, and nothing, not even the deepest ocean floors, was beyond their reach. As if the direct effects of the volcanism weren't devastating enough, the rising temperatures triggered another catastrophic feedback loop. Bubbles of methane gas began escaping from beneath the seabed as rising temperatures melted deposits of this greenhouse gas that had been frozen for millions of years. Methane is at least 20 times more potent than carbon dioxide as a greenhouse gas, and its release into the atmosphere pushed temperatures even higher to nearly 105 degrees Fahrenheit, 11 degrees hotter than before the eruptions began. For 500,000 years, the lava continued pouring out of the earth, eventually covering an area the size of the United States with molten rock nearly 4 miles deep. When the devastation was finally complete, 95% of all species on Earth were gone. The few survivors were those that could eat anything they could find and lived in burrows underground, protected from the hellish surface conditions. Everything else, the giant forests, the massive arthropods, the diverse marine ecosystems, the complex food webs that had taken hundreds of millions of years to evolve, was dead. 250 million years ago, Earth had reverted to something resembling the lifeless planet it had been billions of years earlier. The Cambrian explosion, the colonization of land, the rise of complex ecosystems, all of it had been erased in what amounted to a planetary reset button. But as we've seen throughout Earth's history, even the most devastating catastrophes eventually become opportunities for new forms of life to emerge. The stage was set once again for evolution to begin the long process of rebuilding complexity from the ashes of destruction, though it would take tens of millions of years for life to recover from this greatest of all catastrophes. Let's move to our fourth part of the documentary, The Age of Giants and Cosmic Reset, where we witness how life recovered from the greatest catastrophe in Earth's history and built a world dominated by creatures so magnificent they still capture our imagination today, only to face the ultimate test from space itself. It's been 50 million years since virtually all life on Earth was wiped out by the Permian extinction, and the planet has been transformed into something almost unrecognizable. The air has cleared, temperatures have stabilized, and the acid rain that once burned everything it touched has finally neutralized. Where once there was only death and desolation, vegetation has slowly begun to return. It's now 200 million years ago, and just one supercontinent, Pangaea, stretches from pole to pole across the entire planet. After the trauma of the mass extinction that eliminated 95% of all species, the field has opened for entirely new forms of life to emerge. And one group in particular will seize this opportunity like no other in Earth's history. These are the dinosaurs. The survivors of the Permian extinction have evolved into creatures unlike anything the world has ever seen. These early dinosaurs, called amosaurs, stand 15 feet tall, making them slow and vulnerable compared to what's coming. But nearby, there's already evidence of the evolutionary arms race that will define this era. The Dilophosaurus is small and fast, a perfect complement to the lumbering giants. While one Dilophosaurus might not be able to take down an Amosaurus alone, working together, they can bring down prey many times their size. This cooperation and specialization hints at the incredible diversity and sophistication that dinosaur species will achieve over the coming millennia. The dinosaurs have repopulated the Earth, but no species, no matter how successful, can truly tame this restless, volatile planet. Even as these magnificent creatures establish their dominance, the Earth itself continues to change beneath their feet. The crust is thinning in places, releasing lava and shaking with earthquakes as if the planet is being stretched by some unseen force. This geological activity is happening everywhere, but it's particularly intense near what will one day become North America's eastern seaboard. The Earth's plates are on the move again, and this movement will reshape not just the geography of the planet, but the entire trajectory of life itself. 190 million years ago, the great supercontinent of Pangaea begins to tear apart in one of the most dramatic geological events in Earth's history. A vast slab of land breaks away from the main continent, creating a massive chasm that stretches for thousands of miles. This isn't just a crack in the ground, it's the birth of an entirely new ocean. The chasm fills with water, creating what geologists call the Tethys Ocean, covering what will one day be the Middle East. The formation of this new ocean brings with it dramatic changes in climate and ocean circulation. Currents push nutrients up into the coastal waters, and these nutrients attract fish in unprecedented numbers, millions upon millions of them swarming in the newly formed seas. But as we've learned throughout Earth's history, with abundant life also comes abundant death. The fish and plankton that flourish in these nutrient-rich waters don't live forever, and when they die, their bodies carpet the ocean floor in thick layers. Over the next 10 million years, more layers of rock will bury these dead creatures, and the heat from the Earth's core, combined with the immense pressure from the overlying rocks, will work a kind of geological alchemy. These ancient fish and plankton will be transformed into oil, the black liquid that will one day power our modern civilization. Every gallon of gasoline in our cars, every piece of plastic on the planet, the paint on our walls, the carpet under our feet, even the soap we wash with. Almost all of it originates from this ancient period when the dinosaurs ruled and dead sea creatures accumulated on ocean floors that no longer exist. The breakup of Pangaea continues relentlessly. 180 million years ago, the North American plate is still moving away from the European and Asian plates, shifting about 1 inch each year, roughly the same speed at which our fingernails grow. This might seem impossibly slow, but when you fast forward 35 million years, The cumulative effect is staggering. A completely new ocean forms, along with new continents arranged in patterns we would begin to recognize. The United States breaks away from Africa, and the world as we know it starts to take shape. The chasm between the two continents fills with water, creating the Atlantic Ocean, one of the most important geographical features on our modern planet. And in the middle of this newly formed Atlantic Ocean lies a volcano. Not just any volcano, but part of one of the most spectacular geological features on Earth. Deep beneath the ocean's surface, currents in the Earth's crust continue to move the plates with inexorable force. The entire seafloor tears in two and is pushed up into a massive ridge of underwater mountains and volcanoes. This ridge grows higher than the Himalayas and longer than the Rocky Mountains, creating an underwater mountain range that spans the entire length of the Atlantic. The water here is as hot as molten lava because that's exactly what's forcing its way out from deep inside the Earth. As the lava cools in the frigid ocean water, it creates new ranges of volcanic mountains and entirely new sections of ocean floor. Pangaea breaks apart, and our world rearranges itself into the continental configuration that we know today. It's this constant geological activity that makes Earth restless, creative, and utterly unique among the planets we know. Every time the planet reinvents itself through tectonic movement, volcanic activity, and climate change, its inhabitants must adapt and evolve or face extinction. This dynamic environment creates endless opportunities for life to explore new evolutionary pathways and develop capabilities that would be impossible on a more static world. The dinosaurs proved to be masters of this adaptation. As the continents shift and new oceans form, dinosaur species evolve to take advantage of every available niche. Some, like the ichthyosaurs, make one of the most remarkable evolutionary transitions imaginable. Their reptile ancestors had lived on land, but as the planet changed and new oceanic environments opened up, these animals gradually adapted to life in the water. They developed fins instead of legs, streamlined bodies for swimming, and specialized organs for holding their breath during long dives. This particular ichthyosaur is 20 feet long and can travel at speeds of 25 miles per hour, making it the ocean's fastest creature and most efficient predator. These marine reptiles will rule the oceans for 50 million years, demonstrating the incredible adaptability that allows life to colonize every available environment on the changing planet. But even the mighty ichthyosaurs eventually face competition. Evolution never stands still, and new contenders constantly arise to challenge established dominance. Enter the plesiosaur, a creature that makes the ichthyosaur look almost modest by comparison. Longer than a bus and as heavy as a truck, the plesiosaur possesses jaws 8 times more powerful than those of a great white shark, armed with teeth 12 inches long. These are not just large predators. They are perfectly engineered killing machines, the apex predators of their marine environment. Meanwhile, on land, the dinosaurs continue their reign with unparalleled success. The Earth and its inhabitants have changed beyond recognition from the early days after the Permian extinction. What was once solid ground is now the Atlantic Ocean. The very spot where early dinosaurs like Amosaurs grazed and Dilophosaurs stalked their prey is now hundreds of feet underwater, covered by one of the world's great oceans. But the dinosaurs' world may be different, yet they remain as dominant as ever. They appear invincible, having survived volcanic eruptions, massive earthquakes, and the splitting apart of entire continents. The dinosaurs have thrived for 165 million years by the time we reach this point in their story, making them one of the planet's most successful species by any measure. During this golden age of dinosaur dominance, mammals also exist, but they occupy a very different role in the ecosystem. These early mammals are small, shrew-like animals that pose absolutely no threat to the ruling reptiles. They are prey to the dinosaurs, so they have evolved to live in trees or underground burrows, venturing out only at night when the great predators are less active. From the perspective of the dinosaurs, these tiny, furry creatures are utterly insignificant, barely worth noticing, except as occasional snacks. The mammals survive by staying small, staying hidden, and staying out of the way of the giants that rule their world. Nothing on Earth, it seems, can challenge the dinosaurs' complete dominance over terrestrial ecosystems. But as Earth's history has taught us repeatedly, dominance is always temporary, and the most successful species are often the most vulnerable to catastrophic change. The dinosaurs' very success, their specialization for specific environments, and their enormous size may make them less adaptable when faced with truly catastrophic challenges. And unknown to the dinosaurs as they go about their daily lives of hunting, feeding, and reproducing, such a challenge is already racing toward Earth through the vacuum of space. A large piece of space rock, an asteroid at least 6 miles across, is traveling through the solar system at over 40,000 miles per hour. This cosmic missile is bigger than Mount Everest, and it's heading directly toward Earth with the precision of destiny. The asteroid travels so fast that its impact, when it comes, will be missed in a blink of an eye. But that single split second will change the world forever and bring the age of dinosaurs to an abrupt and violent end. When the asteroid finally strikes, hitting what will become the Gulf of Mexico, the impact is so enormous that it defies comprehension. At the moment of impact, the asteroid's back edge stands at 35,000 feet above the Earth's surface, higher than commercial jets fly today. It strikes with such immense force that it destroys everything it hits, vaporizing instantly and unleashing energy equivalent to millions of nuclear weapons detonating simultaneously. The impact creates a crater over 100 miles across and sends shock waves racing around the planet at supersonic speeds. But the direct impact is only the beginning of the catastrophe. Nowhere on Earth is safe as debris from the collision flies everywhere. Chunks of rock as big as entire city blocks are hurled into space, only to rain back down across the planet like a global bombardment. The blast wave races out from the impact zone like shrapnel from an exploding bomb, flattening forests and killing everything in its path for thousands of miles in every direction. Minutes after impact, even areas hundreds of miles from where the asteroid struck find themselves under attack from boulders raining down from the sky, earthquakes shaking the ground, and tsunamis battering coastlines around the world. But the immediate destruction is only the beginning of the onslaught. The impact hurls so much molten rock and dust into the atmosphere that it forms a plume that spreads out and engulfs the entire planet. The entire sky becomes like a giant heating lamp, raising the Earth's surface temperature to over 500 degrees Fahrenheit. At these temperatures, vegetation spontaneously ignites, turning the planet's forests and grasslands into a global inferno. Even months after the impact, smoke and ash continue to block out the sun's rays, plunging the Earth into a prolonged darkness that makes photosynthesis impossible. Without sunlight, plants die, and without plants, the animals that depend on them begin to starve. 65 million years ago, this cosmic impact brings the age of dinosaurs to an end. These magnificent creatures, which had dominated the Earth for 165 million years and survived every catastrophe the planet had thrown at them, finally meet a challenge they cannot overcome. The asteroid impact has blasted, burned, and starved the dinosaurs into extinction, ending their incredible evolutionary success story and opening the way for entirely new forms of life to inherit the Earth. But as one story ends, another begins. The dinosaurs' demise creates an unprecedented opportunity for the small, insignificant mammals that had lived in their shadow for so many millions of years. By living underground in burrows and tunnels, mammals avoided much of the heat and fires that killed the surface-dwelling dinosaurs. Their ability to eat almost anything, from seeds and roots to insects and carrion, allows them to survive in the harsh, post-impact environment where more specialized feeders perish. They are the unlikely inheritors of the dinosaur's crown, and with the great reptiles gone, mammals finally have their chance to emerge from hiding and explore the ecological niches that had been denied to them for so long. The age of giants has ended, brought to a close not by gradual climate change or slow evolutionary replacement, but by a single moment of cosmic violence that reminds us how precarious life's hold on this planet really is. The dinosaurs' 165 million year reign demonstrates both the incredible success that evolution can achieve and the vulnerability that even the most successful species face when confronted with truly catastrophic change. Their story is a testament to the dynamic, ever-changing nature of our planet and the constant interplay between geological forces, cosmic events, and the persistence of life in finding new ways to survive and thrive in an unpredictable world. Now we are moving to our fifth and last part of the documentary, titled The Final Steps to Our World. After an incredible journey through billions of years of Earth's formation, life's beginnings, mass extinctions, and the rise and fall of mighty creatures, we are finally closing the chapter with how our planet took shape into the home we recognize today, and how we, humans, came to be part of this magnificent story. The story continues 47 million years ago, in what would one day be Germany. Here, in an ancient volcanic crater lake that preserved life with exceptional clarity, emerges Darwinius Macillae, better known as Ida. Though she looks nothing like us, Ida represents a key early link in our mammalian ancestry. This small primate had bigger eyes and a more developed brain than her predecessors, and scientists today believe she may be critical to understanding the evolutionary steps that ultimately led to humans. Through Ida, we glimpse a distant mirror of ourselves, a hint of the long chain that connects ocean bacteria to walking fish, early mammals, and eventually, us. The lake that preserved her sat on a volcanic crater that belched out noxious gases, eventually killing her, but also preserving her remains in the oxygen-depleted depths for millions of years. When her fossil was finally discovered, this primitive primate helped piece together the beginning of our own story, the story of human life. The Earth at this time bears a strong resemblance to the planet we call home. The atmosphere's composition, temperature hovering around a comfortable 75 degrees Fahrenheit, and day length just under 24 hours all speak to the gradual stabilization of global systems that had been chaotic for so long. But the planet was still young in many ways, and dynamic forces continued to shape its surface and the life upon it. We're closer to understanding how everything we've witnessed, from ocean bacteria through walking fish and subterranean mammals, leads directly to us and to understanding how our planet was made into the world we know. Over millions of years, the slow but relentless movements of tectonic plates continued to shape the continents and mountain ranges we know today. One of the most significant events was the collision of the Indian plate with the massive Asian plate. This wasn't a quick crash, but a titanic struggle lasting millions of years, with neither plate winning the battle easily. As they buckled against each other, the ocean floor contorted upward along a 1,500-mile line, creating a vast mountain range that rises over 27,000 feet into the sky. These are the Himalayas, and among them stands the highest mountain of all, Mount Everest. Its summit reaches into the Earth's jet stream, the same altitude where airplanes fly today. These mountains aren't just majestic landmarks. They serve as a vast water tower for our planet. When the snow on their peaks melts, it feeds mighty rivers like the Ganges, Indus, Yellow, and Yangtze. The Himalayas supply water for almost half the world's population today, reminding us how geological events millions of years ago continue to influence and sustain life now. This is the beauty of our planet's interconnected systems. Nothing exists in isolation, and events separated by vast stretches of time continue to echo through the present. 20 million years ago, our planet looked almost exactly as we know it today, with every continent and every ocean in its familiar place. But one crucial element was still missing: the human race. For humans to evolve, something fundamental needed to change, and that change came from an unexpected source. Along the African coast, a great rift began to open up, stretching nearly 4,000 miles, with mountains growing along its edge. This massive geological feature would prove to be one of the most important developments in human history, though no one could have predicted it at the time. This ape-like creature living in the African trees might have stayed there forever, but its world was changing around it. The growing mountains acted like a massive wall, preventing moisture from the Indian Ocean from passing over the land. The climate became hotter and drier, and the lush rainforest gradually transformed into an arid savanna. This dramatic environmental change altered the creature's habitat completely, forcing them to search further and further for food and water. As the trees became scarce and the distances between food sources grew longer, these early ancestors faced a crucial evolutionary moment. Soon, they stopped dragging their knuckles like apes and began to stand and walk upright on 2 feet. This was the most important step in the human story. The mountain range, created by tectonic forces, could be the very reason humans walk on 2 feet today. The random movement of 2 massive geological plates may have kick-started a chain of events that led directly to the first humans. It's remarkable to think that something as massive and seemingly unrelated as continental drift could have such a profound impact on the development of our species. But this is exactly how our planet works. Everything is connected across vast scales of time and space. Here, we see early humans for the first time, a man and child in a scene that looks very much like today, except this moment occurred 1.5 million years ago. They belong to an early species of human called Homo erectus. and these are the first footprints that look like our own. In these fossilized tracks, we can trace the beginning of something extraordinary. Civilizations past and present, everyone that's ever lived, the greatest inventions, the most brilliant ideas. Human history in all its complexity and splendor begins here and now with these first upright steps across the African landscape. The climate continued to change, as it always has throughout Earth's history. Around 70,000 years ago, sea levels fell dramatically, and the gap between Africa and Arabia shrank to just 8 miles. The Red Sea became narrow and shallow enough for a small group of early humans to cross out of Africa and into the wider world. These weren't modern humans as we know them, but another later species called Homo sapiens. Scientists believe that the entire world beyond Africa was populated by descendants of just 200 individuals who made this crucial journey. It's staggering to think that every person outside of Africa today can trace their ancestry back to this small group of pioneers who took advantage of a temporary land bridge created by changing sea levels. Over time, our ancestors multiplied and spread out across the globe, to India, across Asia, and into Europe. They encountered new environments, different climates, and countless challenges, but they adapted and survived. However, while humans were spreading north, a giant wall of ice was traveling south. Europe, 40,000 years ago, presented early Homo sapiens with a world that was rapidly changing. It should have been the height of summer, but temperatures were dropping, plants were becoming frostbitten, and rivers were freezing solid. Natural changes in Earth's orbit, carbon dioxide levels, and the flow of warm water around the planet had conspired to lower the Earth's temperature significantly. The Earth and its inhabitants were entering an ice age, one of many that have shaped our planet's history. Glaciers as high as skyscrapers began to creep over the northern hemisphere at about a foot per day. While that might not sound fast, these slow but powerful ice sheets were unstoppable, sculpting the landscape and gouging out great depressions that would become lakes when the ice finally retreated. The planet would never look quite the same again after this icy transformation. Around 20,000 years ago, the glaciers ground to a halt after covering much of the northern hemisphere with ice sheets up to 1.5 miles thick. With trillions of gallons of water locked up as ice, sea levels fell dramatically around the world. This drop in ocean levels revealed something remarkable. A strip of land emerged from between Siberia and Alaska, creating a bridge between two vast continents. This land bridge became a gateway that allowed humans to travel from Asia to an entirely new world, the Americas. These were the last great continents to be colonized, representing the final great human migration, and these travelers became the first Americans. The Ice Age couldn't last forever, and around 14,000 years ago, the changes that had triggered this frozen period began to reverse. As the massive ice sheets started to retreat, they revealed a very different northern hemisphere than the one they had covered. The huge depressions that the glaciers had carved out filled with water to become North America's Great Lakes, some of the largest freshwater bodies on the planet. By 6,000 years ago, the ice had retreated back to the poles, toward the Arctic and Antarctic regions where much of it remains today. After a journey spanning 4.5 billion years, we had finally arrived home. This is our world, our time, shaped by every cosmic collision, every volcanic eruption, every ice age, and every small evolutionary step that came before us. The planet's incredible story, helps us understand how and why everything around us is here today. From the skies above to the water that sustains all life, from the ground beneath our feet to the miraculous phenomenon of life itself. Each element of our world tells a story of deep time and incredible change. The water we drink may have arrived inside ancient meteorites, traveling millions of miles through space before reaching Earth. The iron in our blood was forged in the hearts of dying stars billions of years ago. The oxygen we breathe was first produced by tiny bacteria that learned to harness the power of sunlight. Even the coal and oil that power our civilization are the compressed remains of plants and animals that lived hundreds of millions of years ago. Their ancient energy now serving our modern world. It's a chain of catastrophes and coincidences that has created a spectacular result. Each triumph and disaster along the way was a necessary step leading to here, to each and every one of us right now. From the violent birth of our planet through cosmic collisions to the delicate balance of conditions that allows complex life to flourish, our existence represents the culmination of an almost impossibly unlikely series of events. But Earth's story isn't over, not even close. This incredible journey through deep time is only half the story, with much more yet to come. Our planet will live for at least another 4.5 billion years, and during that vast expanse of time, more wonders, more challenges, and more strange creatures lie ahead for our restless and creative world. The continents will continue to drift, new mountains will rise while old ones erode away, and life will continue to evolve in ways we can barely imagine. We are living participants in this ongoing story, not just observers of the past. The next chapter of Earth's incredible tale is still being written, and we have become part of the authorship. How we care for our planet, how we respond to environmental changes, and how we grow as a species will all become part of the geological record that future inhabitants might one day discover and study, just as we have studied the traces left by those who came before us. Thank you for joining us on this extraordinary journey through time here at the Sleep Lab. If you've enjoyed exploring the incredible story of how our planet formed and how we came to be part of it, please don't forget to like this video and subscribe to our channel. Your support helps us continue creating these thoughtful explorations into the profound mysteries of our universe, designed to both educate and help you find peaceful rest. Until next time, sleep well, knowing that you are part of the most amazing story ever told, the story of Earth itself.